Thank you, Mr. Chairman. Good morning, everyone. My name is Keisuke Takada from Kyoto Institute of Technology, Japan. Today, I'd like to talk about a new biosensing by dielectric dispersion analysis of interaction between lipid membrane of liposome and target biomolecules up to 20 GHz range. First, I will explain a background. We have used liposome supermolecule as a sensing element. What is a liposome? It is composed of closed shape of phospholipid membrane and known as an artificial cell membrane model. This shows a TEM image of liposome. Liposome is comprised of phospholipids consisting of hydrophobic group and a hydrophilic group. In this work, we use liposome with controlled diameter around 100 nanometer. Liposome has characteristics to interact with important biomolecules, such as protein. Therefore, we have used liposome as a sensing element for detection and identification of the biomolecules. This is an objective of my research. The state of hydration water on liposome membrane generally changes by the interaction. So, we measure the permittivity dependent on the hydration water by DDA and evaluate the interaction between liposome and target external biomolecules. This is a brief outline of my presentation. At first, a DDA and its measurement method, and second, the measurement of liposome by DDA, and third, the measurement of the interaction between liposome and biomolecule, especially when we measured the dependence on CAB or cholesterol concentrations. And fourth, we considered the mechanism of a variation in the electric relaxation, and finally we will summarize. Next, a measurement method of DDA. DDA is the dielectric dispersion analysis. We measure the permittivity of liquid solution from 45 MHz to 20 GHz using a network analyzer. And this shows a measurement system. An open-ended coaxial probe is connected to the network analyzer through a coaxial cable. And the probe is inserted into the 100 microliter liquid solution in this test tube. This is a photo of a coaxial probe cross-section and comprised of outer conductor and inner conductor across PTFE insulator. Next, the electric relaxation of liposome. Permittivity changes by the electric relaxation of hydration water on liposome membrane when measuring the liposome suspension. This is an illustration. Of hydration water molecules on liposome membrane. The hydration water is classified as bound water and free water, depending on closeness to the liposome membrane. As a DDA result, permittivity decreases with increasing frequency, like this figure. At the dielectric relaxation, permittivity decreases, and we define this dielectric relaxation width as delta epsilon, and it is possible to consider the state of hydration water on liposome by evaluating this delta epsilon. We use the DDA for DPPC liposome. We use DPPC liposome in this research, and DPPC is abbreviation of 1,2-dipermethyl SN-glycerol 3-phosphocholine. This is measurement result of DDA, that is frequency dependence on permittivity. We use the liposome with concentration of 30 millimolar and molecular diameter around 100 nanometer. As you can see this figure, permittivity decreases with increasing frequency. And you can see here the dielectric relaxation regions in higher frequency regime, and we find a new dielectric relaxation that has not been reported yet. We defined these relaxation regions as region 1, 2, and 3, respectively from lower frequency side. Since relaxation frequency of bulk water is around 25 GHz, the existence of regions 2 and 3 means that water molecules are bound in two different mechanisms. As will be shown later, by the interaction with target biomolecules, we can observe the interaction by the measuring relaxation with delta epsilon and the relaxation with change delta delta epsilon. Here, we introduce biomolecules of cholesterol and CAP as the target molecules to liposome membrane. And cholesterol, it is one of an important organic compound. This is the image of cholesterol existence seen as yellow part and its molecular structure. Cholesterol absolutely exists in biological membrane and it is a biogenic molecule. CAP stands for carbonic anhydrase from bovine and it is one of a protein. This is the image of CAP molecular structure. And generally, CAP is used to control pH by carbonic anhydrase. Next, we will show the measurement result of the interaction between DPPC liposome and added cholesterol. These are the results for region 2 and region 3. In these figures, the vertical axis shows change in relaxation with delta delta epsilon and the horizontal shows added cholesterol concentration. Cholesterol is in dispersed state when less than 33 mol%, while it is in aggregation state more than 33 mol%. Therefore, in the present case, cholesterol is always in dispersed state. As you can see from these figures, delta delta epsilon for region 2 and 3 decrease and saturate with increasing cholesterol concentration. We find that this tendency is similar to the results of leakage current microsensor in our previous paper. It is especially observed that delta delta epsilon is larger by about 4 times for region 3 than for region 2. This indicates that the major relaxation phenomena occurs for region 3 at higher frequency. Next, we also introduced the interaction between DPPC liposome and CAP protein. These figures show also delta delta epsilon versus target biomolecule concentration. Similar to the former result, it is observed that delta delta epsilon decreases with increase in target concentration. Compared to the former case with cholesterol, delta delta epsilon is larger for region 2 by about 3 to 5 times than for region 3. These tendencies are opposite from the case with cholesterol. We consider mechanism of decrease in delta epsilon. The decrease depends on the target biomolecule concentration. This indicates that the number of bound water molecules decrease with increasing target concentration. It is natural to estimate that the interaction becomes larger with increasing concentration the target biomolecule. This illustrates shows the example of the mechanism. In the interaction, target the external biomolecule approaches and excludes bound water molecules on liposome. As a result, the number of bound water molecules decreases and the corresponding relaxation width decreases. We think that these situations are supported by Onsaga's equation. This illustrates again the bound water molecules on liposome membrane. From the mentioned DDA results of CAP and cholesterol, the interaction occurs with different manner between CAP and cholesterol. That is, it is estimated that CAP excludes dominantly the bound water of region 2, while cholesterol excludes the bound water of region 3, where the water molecules are bound stronger for region 3 than region 2 than for region 3. And this might be related to the difference in mass between them. And this is summary. In DD result, we find a new dielectric relaxation region, possible trace of bound water on liposome membrane. And by adding biomolecule, cholesterol or cap to liposome, and first, the electric relaxation width is decreased with increasing target biomolecule concentration. This is because that bound water molecule on liposome membrane is excluded. And second, the relation of relaxation width between regions 2 and 3 are different between the two different biomolecules. The interaction manner to exclude the bound water molecule is different between the two cases with cholesterol and cap. And acknowledgement. Thank you for kind attention.